Okay, so in this video we're going to discuss the chain rule in multiple variables. So let's do a real quick recap of the flip class video. So let's suppose we have some function z is equal to f of xy, and let's suppose x is a function of t and y is a function of t as well. So let's recall from our linear approximation that if we looked at the delta z, remember this was approximately, so when we're looking at our differentials from the linear approximation material, this was delta z delta x plus delta z delta y. And so that means our change in z here is approximately delta z delta x plus delta z delta y. So now we can use differentials from one variable to say, well, this was approximately dx, which was dx dt, which we could also write as dx dt delta t, and delta y was approximately dy, which was dy dt, which we could also write as dy dt delta t. So this is differentials with one variable, so the one variable here being, our independent variable here being t, and this was differentials with two variables, or independent variables there being x and y. So that means if I combine these things, I have delta z is approximately delta z delta x, and then I can put dx dt delta t plus delta z delta y dy dt delta t. And now let's go ahead and divide both sides by delta t. So I have delta z delta t is approximately delta z delta x dx dt plus delta z delta y dy dt. And so now if we let delta t go to 0, the left-hand side here becomes dz dt, and then we end up getting an equality here, and we get delta z delta x dx dt plus delta z delta y dy dt. And so this was our chain rule. In this case, we saw it in the flip class video. And the way to remember this was we drew a diagram. So we said z is a function of x and y, and then these are each a function of t. And then we label our diagram. So since z is a function of x and y, there's two variables on the one below it. We put partial derivatives here. And then since x and y are a function of only one variable, there's only one variable on the line below. These are just regular derivatives. And so then if we look from z all the way to t, there's only one variable on the line at the bottom, so it's a regular derivative. And then we follow each path down. So if we go down this path, we get delta z delta x times dx dt plus delta z delta y dy dt, following the other path. And we saw more general versions of this in the flipped class video, but let's try an example. So we'll do one just example with kind of just the functions, and then we'll do some applied examples as well. So let's let, say, z be x squared y minus 2 sine xy. Let's let x be, say, e to the t squared, and y be cosine of 2t. And let's find dz dt. So we need to take a bunch of derivatives here. So we need delta z delta x. So this is going to give me a 2xy minus 2 cosine of xy, and then the derivative inside, which is y, delta z delta y. Now I'm going to get an x squared minus 2 cosine of xy times x. I need dx dt, so this is going to be et squared times 2t, and dy dt is going to be minus sine of 2t times 2. So just taking a bunch of derivatives there. And now we can put all these together. So dz dt, this is delta z delta x, dx dt plus delta z delta y, dy dt. And now we just fill all of these in. So I have 2xy minus 2 cosine xy times y. And then this is times 2t e to the t squared plus x squared minus 2 cosine xy times x, and then this is times minus 2 sine of 2t. And then generally we like to try to get these all back in terms of just t's here. So this is 2 e to the t squared, and remember our y here was cosine of 2t, minus 2 cosine, and so I have e to the t squared cosine of 2t times cosine of 2t, and then this whole thing times 2e to the t squared plus I have e to the t squared squared minus 2 cosine e to the t squared cosine of 2t times e to the t squared. It's minus 2 sine of 2t. So in this case, we could have also just plugged these values for x and y into our original equation and then just taken the derivative with respect to t. That would have also worked. But we can't always do that with every chain rule example. So it's good to know how to do both ways. Okay, so let's try some word problems that use chain rule. Okay, so for the capacity C of a communications channel, such as a telephone line, to carry information depends on the ratio of the signal strength S to the noise N. Let's say for some constant K, our formula here is C is equal to K times natural log of 1 plus S over N. Let's suppose okay, so our noise and our signal strength are functions of the time measured in seconds. And these equations are going to be S of t is 4 plus cosine of 4 pi t, and N of t equals 2 plus sine 2 pi t. So let's say, what is dc dt 1 second after the transmission started? let's say, does the capacity increase or decrease at that instant? Okay, so the first thing we can note is just our formula we just have been using. So this is delta C delta S ds dt plus delta C delta N dN dt. And now we have the formulas for C, S, and N, so we'll just do these calculations. So notice this is the C is the K times ln of 1 plus S over N. So I get K over 1 plus S over N, and then the derivative of what's inside, which is just 1 over N. The first part of this will be the same, but now since I'm differentiating with respect to N, I'm going to get minus S over N squared. And then ds dt, taking the derivative of this 4 plus cosine of 4 pi t. So this is minus sine of 4 pi t times the stuff inside, derivative of what's inside, which is 4 pi. And then we have sine of 2 pi for the other one. So dn dt is going to be 2 pi cosine of 2 pi t. So then we want to evaluate these at t equals 1. So notice first, s of 1 is 4 plus cosine of 4 pi, which is 5. N of 1 is just 2. So just notice sine of 2 pi is 0, so we just get a 2 for that. So delta C delta S at t equals 1 is k, and I have 1 plus 5 halves times 1 half. Delta C delta N at t equals 1. So I'm going to have this is k over 1 plus 5 halves. And now I have times minus 5 over 4. And then ds dt, t equals 1. So at t equals 1, I have sine of 4 pi, which is 0. So this one's just 0. dn dt at t equals 1 is just 2 pi. So when I do dc dt, I fill these in, and I have the k over 1 plus 5 halves times 1 half, and then that's multiplied by 0 plus k over 1 plus 5 halves times minus 5 fourths times 2 pi. So if we simplify this, this becomes minus 5/7 pi k. And now I don't remember whether we said k is a positive constant. Let's say some positive constant. So then this is less than 0. So the capacity is decreasing because its derivative is negative after 1 second. Okay, let's try one more example. Okay, so student A's score on a weekly quiz, which we're going to say is denoted by S in points, is a function of both the number of hours spent studying and the number of problems that they solve per week. So the score S goes up 2 points for each additional hour spent per week studying. The course materials. And the score goes up 3 points for each additional 5 problems solved during the week. Okay, so the score goes up 2 points for each additional hour studying, 3 points for each additional 5 problems solved, and the number of hours that they've spent studying the course materials has been decreasing at 1.5 hours per week. Let me give you a second to copy some of this down in case you're taking notes. Okay, so what do we want to ask about this? Okay, the student score. Let's add this on there. Does not change from week to week. Okay, so what are we going to do with this information? Let's find the value of dp dt, where t is the time in weeks. Make sure we include some units. And for the second part, say what can the student learn from the value of the derivative in part A. Okay, so for part A, we have S is a function of H and P. So from the setup, we know that the value of S goes up by 2 for every additional hour spent. The value of S goes up by 3 points for every 5 problems solved, so 3/5 is our ratio. And then finally, dH, dt, the number of hours, we're told is going down by 1.5 hours per week. So this would be minus 1.5. And then we also are told the student's score does not change from week to week. So that means that ds dt has to be equal to 0 because it's not changing. So if we use chain rule, we know ds dt, which is equal to 0, is delta s delta h dh dt plus delta s delta p dp dt. And now we're interested in finding dp dt, so we'll solve this equation for dp dt, and I get delta s delta p dp dt is equal to negative delta s delta h dh dt, or dp dt is equal to negative delta s delta h dh dt over delta s delta p. And so now we can fill these things in. So I have minus 2, and I have 2 minus 1.5 all over 3/5. And so this is 3 divided by 3/5, which is 5. And then note the units of p are problems, and the units of t are weeks. So then the question is, what do we learn from this? So she needs to increase the number of problems she does per week by 5 problems to offset studying 1.5 hours less per week.